Okay, so yes, so I hope the screen is visible to all of you. So we have completed the RE equivalent model of the BJT. We have used that RE equivalent model to solve for the input impedance, output impedance and the voltage gain of several BJT configurations. Now as I was going through the configuration, and as you have been able to observe, if you have observed closely, that there is no particular need to memorize everything, because in every configuration I am employing the basic KVL, KCL, Ohm's law only. So if you are confident in your usage of these basic laws of electrical engineering, then you will be able to solve any of these configurations very easily. One thing only, that there are some assumptions or approximations involved, which come from the various values of the different resistances, also from the transistor characteristics. So these approximations you have to remember by observing them, how we are applying the approximations, and that you will get an idea on how they are getting used. So if you are given a new circuit to solve, a new network to solve, which does not look familiar to any of the networks which I have discussed in the class, then also you will be able to go ahead solving those networks. So you must develop that confidence in yourself, and that can only be developed if you practice a lot. So you should practice from the books. There are many solved examples, also tutorial problems are being given, and they are all also getting collected and getting distributed to the class, so you can also practice from those problems. So these are the typical type problems which is expected to challenge you in exams and also in practical circuit designing, if you actually would be doing that sort of a work in future. So today we would go into the hybrid equivalent model, and of course another thing that we also covered are the cascaded BJT systems. By considering the entire BJT, one configuration of the BJT as a two-port network, we can place such two-port networks in cascade and solve a more complicated network. So we don't have to solve a complicated network all at once and confuse ourselves in the process, but we can identify each subpart of the network. So each BJT we can identify how they are configured, whether it is a common emitter, whether it is a common base, whether the emitter resistance is bypassed or not. All these things we can notice by just observing the circuit, and then we can employ a two-port network in place of that BJT. So in this way we can have a connection of different two-port networks, and then we can solve the cascaded system in the manner that we already discussed, how we actually solve cascaded two-port systems. So that also we had discussed. Today we will probably I will try to end the BJT part today. There are two more models which we need to study. These are models which the hybrid equivalent model and the pi model. So these were used earlier. Nowadays RE equivalent model is the most widely used model, but we also need to study what these models are because in data sheets you might find the hybrid parameters given. So the hybrid parameters, how do they relate to the RE equivalent model parameters? This also we need to understand. So in the data sheet, which is the data sheet of the BJT, where the BJT you are working with, you will be supplied the hybrid parameters. But if you are if you are trying to analyze it using the RE equivalent model, then you have to understand how the hybrid parameters relate to the RE equivalent model parameters. Okay, so in the RE equivalent model, what are the parameters? The parameter is simply the RE resistance. That is the only parameter, and that is calculated as 25 millivolt divided by IE. And the other parameter is the beta or the alpha, the gain, and there is, of course, there is this output resistance RO was there, which is the slope of the collector characteristics curve, but that is quite high and often we neglect that resistance and consider that as an open branch. But in hybrid equivalent model, how we are proceeding, let us see. So in hybrid equivalent, just forget about everything about the RE equivalent model for the time being. Just erase everything from your memory for the time being. Just consider that the BJT is, after all, a 3-port system. There is a base, there is an emitter and a collector. 3 ports are there. Between 2 of these ports, the input signal is applied, and from 2 of the ports, the output signal is extracted. So one port is common, and that port which is common is actually called the common base or common emitter, like that. So normally we have seen a lot of common emitter configurations. So in that case, the base emitter port is the input port and the collector emitter port is the output port. So whichever be the input port or output port, at the end of the day, it is simply there are 3 ports, and one port is common to both the input and the output. So in this diagram, you can see that such a system can be considered as a 2-port system again, with one port being common to both the input and the output. Now what we do, we employ very general equations of 2-port systems to find out the what is called the hybrid equivalent model of the BJT. These equations that you see are very typical and general equations of 2-port systems. What do I mean by that? I mean that whenever you have a 2-port system whose inside you don't know what is there inside, you don't know that, but you only know the outside variables, the external variables, the input side Vi and Ii, in the output side V0 and I0. These variables you only know, and these variables you can measure. You can measure by employing a voltmeter and ammeter. You can actually measure these variables. So these variables are known and measurable. What we do when we study, you will also be studying 2-port systems. Actually, when you will be studying the 2-port systems, you will see that these variables are related to each other through linear relationship, through some linear relationship. If this is a linear system, if this system which is inside this blue box is a linear system, then you can relate the input and output using linear relationships, and the relationships that are employed typically are these, what you see here in the right hand side. The input voltage is equated as a linear relationship of the input current and output voltage. The output current is related as a linear relationship of the input current and output voltage. As such, what we are seeing here in these two equations, as if whoever has modeled the two-port system by these two equations, they have considered the input current and output voltage as the independent quantities, and input voltage and output current as the dependent quantities. They have considered it in this way. That is, this is the way that things has been defined, and we have to start working from this point. This is as per convention. You could have said, no, I want to define V0 as a dependent variable, Vi and Ii as the independent variables. That could have been done, of course, that could have been also done, but this is the way it has been defined, and this is the way that the convention has continued from this way, and we continue with this only. So please remember what is in the input side and what is in the dependent side, which is the right hand side, and what is in the independent side, which is in the, sorry, I am saying in the opposite way. What is the dependent is in the left hand side, and what is independent is in the right hand side. So please observe this and remember this. This has to be remembered. After that, you see, this is very simple. The first parameter is H11, next is H12, the third is H21, and then H22. So this is very simple to understand why they are named like this. One thing you have to remember, the first independent variable is IEI and the second one is V0. It is not the other way. So H11 is associated with IEI, then H12 associated with V0. So if you get an understanding of this, then if suddenly someone asks you what is H21, so you will have a picture in your mind that I0 is H21 II plus H22 V0. So H21 is associated with II and trying to relate I0 with II. So H21 is trying to relate I0 with II. Similarly, H12 is trying to relate V0 with 2 VI. H12 is trying to relate V0 to VI. So these things should get familiar in your head. Okay. So now, okay, let me clarify one thing. I told you that this modeling can be done only if the system inside is a linear system. Only if the system inside is a linear system. However, we had started this entire class, course with the idea that we are studying nonlinear elements in a circuit. So obviously BJT is a nonlinear element. However, we are only concerned with that part of the behavior of the BJT which is linear in nature. When does that part of the behavior appear? When the BJT is, when the Q point of the BJT is in the active region. When the BJT is biased in the active region, then only then the linear behavior appears. Otherwise, in the saturation region or cutoff region, it is not linear behavior. Only in the active region, the BJT is behaving as a linear element. We are trying to capture that behavior only with this equivalent model. Please remember this. When the BJT is working in the active region, then only we are able to utilize the linear behavior of that element, and that linear behavior is basically a behavior of amplification. Only when it is in the active region, the output current is beta times the input current, not anywhere else. Please remember this. And this is the linear behavior, that the output current is some beta times the input variable, where beta is a constant. So the output current and the input current are linearly related in the active region. This is the linear behavior. So if someone tries to quiz you about what is the linear behavior of a transistor, why why this linear modeling could be applied. So remember this, what I said right now, this is the answer. Okay, so this is a conceptual thing that you need to clarify in your head. Okay, so going ahead, let us now work with these equations. We are trying to understand what these H11, H12, these things mean actually. Very easy to see what they mean. H11 is what? H11 is nothing but Vi by Ii when V0 would be 0. So if V0 is 0, H11 is Vi by Ii. So you see, we are defining it in that light only. H11 is Vi by Ii when V0, this means given, this line means given or when. So given a V0 equal to 0, that in words would mean V0 equal to 0 means the output is short circuited. So this is short circuit input impedance. This is an input impedance, V by I is an impedance, but this impedance is in the input side in the condition that the output is short circuited. We don't need to write output short circuit input impedance, we don't need to write that, because if the input is shorted, there is no concept of impedance appearing anyway, because Vi already 0. Okay, so it means that this short circuit is in the output. One does not need to clarify that anymore by putting an additional word here. So this means that we are trying to calculate the input impedance when the output is short circuit. Similarly, what would H12 mean? In H12 Ii would be 0. Ii should be 0. That means this input side must be open circuit. There should be no source connected here. Only then Ii can be 0. So when the source is not connected, then we are trying to figure out what is Vi by V0. Please note this, this is not V0 by Vi which we were used to figuring out the gain of the transistor, but this is Vi by V0 in the condition that there is no source connected. So this is open circuit reverse transfer voltage ratio. When we say transfer voltage ratio, we mean input to output, but when we say reverse transfer voltage, we mean output to input. That means this is Vi by V0. Open circuit obviously lets us know that this is open circuit in the input side, because the transfer is coming from the output side. So output side cannot be open. The transfer is happening from the output side to the input side. So output side cannot remain open. The open is in the input side. This has to be understood. Similarly, H21, you see H21 is what? When V0 is 0, again a short circuit. So short circuit, what it will be? It is I0 to H21 is I0 by II. So II, the input current, is getting transferred to the output current. So it is a forward current transfer. It is a reverse transfer voltage. This is forward transfer current or forward current transfer ratio. So in short circuit, when the output is short circuit. H22 would be II equals to 0, again open circuit, and this is I0 by V0. So it is a conductance or admittance in general, impedance admittance. So this is output admittance. I0 by V0 is output admittance in the event when the input is open circuit. So it is open circuit output admittance. So I hope these terminologies are now more clear, and if someone asks you what exactly is H21, you would be able to say that it is short circuit forward current transfer ratio, all of that. If someone tells you tell me which is the open circuit reverse transfer voltage ratio, you should say that it is H12. Okay. So these terminologies, please pay attention and relate this in your head. I hope that I was able to make you understand this. But if there is any doubt in this place, if I need to repeat, please tell me at this moment only, so I will again go through it. Just look at the equations and these terminologies, spend some time, and if you are still not able to understand, I will again tell you. Okay, so I hope that things are clear. So what we will now do, this is a general equation, general model, general equation of a two-port system. But now, since we know the definitions of these things, what these actually mean for the system which is inside. So this is short circuit input impedance of the network which is inside. This is open circuit reverse transfer voltage of the network which is inside. So we know what these are. These H11, H12, H21, H22 are for the network which is inside. So inside what is there? Inside there is a BJT. Inside there is a transistor. So if what would be the short circuit input impedance of the transistor? Okay, what would be the open circuit reverse transfer voltage ratio of the transistor? So if we try to use these parameters in order to draw up a equivalent model of the transistor, then that equivalent model would be drawn in this way. So in the transistor, some current, input current comes inside, and sorry, this is not for the transistor, this is for the two-port system in general. This diagram is for the two-port system in general. So this you see now that I can actually write down this HI, HR, HF, H0. So we have simply replaced this H11 with HI, H12 with HR, H21 with HF, H22 with H0. Why so, you will just understand, but using these symbols now you can draw up this network, which is nothing but the same two-port network. But whatever was inside there may be very complicated arrangement of elements. Whatever was inside, we can simply replace them with these four elements when we are able to calculate these, and these are very easy to calculate because these are nothing but the ratio of some variables which we can measure directly. These H parameters, they are called the hybrid parameters. These are nothing but ratios of system variables which we are able to measure. So we can calculate them given any system. You have any system, you identify the input port, you identify the output port. Now you do a few experiments and you are able to obtain the H parameters. I am pretty sure this experiment is there in some course of your power systems, because I remember doing this experiment when I was a UG student. This is very simple experiment. You only need to measure the input current and measure the currents and the voltages at the ports, input port and output port. You get the H parameters. Once you obtain the H parameters, the entire complicated network which is inside those two ports can be replaced by this arrangement of elements, and you can do your analysis after that using this network. This is same as the network for which you have calculated the H parameters. This is the beauty of two-port networks, and this is the beauty of the hybrid equivalent model of a two-port network. I hope you appreciate this this thing what we have been able to do. So we have been able to put away the complicated network and employ a very simple network inside. And as the definitions had we had obtained, you simply see that hi is here, this hi is nothing but h11, because if your v0 is 0, then hi is the input impedance. So h1 would be hi would be h11. What is hr? hr, you see, when the input current is 0, then the input voltage vi is nothing but hr v0. So it is hr would be h12. Similarly, what is hf? hf is your h21, and h21 is this. When so suppose your v0 is short circuited, then your what happens then? Then this h0 gets short circuited. So whatever is I0 is flowing through your HFII. I0 becomes HFII. So HF is nothing but H21. And the last one, H0, when II is 0, that means this branch gets open now, then your I0 is H0 into V0, and H0 is then H22. So once you calculate H11, H12, H21 and H22 by doing some experiments on the two-port network, on a network at its two ports, you now can figure out what is H1, HR, HF, H0 and use them to replace that entire network with this very simple network. And what are these called? HI is called input resistance, HR is reverse transfer voltage ratio, HF forward transfer current ratio, H0 output impedance, HO is output conductance. That's why this suffix is IRFO. You can understand that. So we will employ this circuit. This is the hybrid equivalent circuit. We will employ this circuit to replace a BJT. Anything can be replaced. Any two-port network or any two-port element, any two-port device can be replaced by this circuit. So we will replace the BJT with this circuit. So now most common configurations that we have seen in the BJT are the common emitter and the common base. So whether it be common emitter, whether it be common base, it does not matter. Both are two-port systems. So the same circuit is there. It is the same circuit which is coming here. What is the only difference? The HI calculated for this and this would obviously be different. The HR will also be different. HF, H0 all will be different. The values of these HR, HI, H0, HF, they will be different. But the arrangement of these elements will remain the same. Arrangement of these elements will remain the same. So to distinguish between the HI of emitter, common emitter and common base, we just add a new suffix E or B with the hybrid parameters. This identifies that the entire system is common emitter. Here it is common emitter. Here it is common base, because another suffix B has come in picture. common base. Okay, rest of the things are same. And just note one thing, normally we write the write HOE here in this resistance, but HO is basically the conductance value, so the resistance value is basically 1 by HO. Please keep that in mind. Normally we can write it as HO also, but it is a conductance value, so you have to be careful there. So once we arrive at this, so this is the actual hybrid equivalent model of the BJT. But as you have already noted that we don't like to work with actual models or actual things, we always going for approximation when we are working in this course of analog electronics. We are always going to approximation, and approximations are quite valid. That's why we are going to approximations. And what is the approximation here? What we find that the HR and H0 values for both the common emitter and common base configurations are sufficiently small. Where are these HR and H0? You see, HR is here and H0 is here. H0 small means this resistance is quite high. HR small means this voltage between this point and this point is quite small. So we can neglect this HR H0, and that does not affect the Zi, Z0 and AV of this two-port system. Remember, the two-port system will also have this Zi, Z0 and AV. Okay, the Zi, Z0 and AV are the things that concern us, because these are the things that help us to utilize the two-port system in cascade and to understand the voltage gain when the BJT is working as an amplifier. So these are the quantities of concern for us, and if HR and H0 are neglected, it does not affect this Zi, Z0 and AV to a great extent. That's why we can come to the approximate model. Sorry, something. We can come to this approximate hybrid equivalent model, where you see the HR is made 0, and when the HR is made 0, this branch is shorted, and when the H0 is made 0, this branch gets open. So what we are left with from this? We are left with this. From this we are left with this. Does this not look familiar to you? Just remember the RE equivalent model. In the RE equivalent model, there was simply one resistance and a current source. There was an output resistance which was neglected. So with that in mind, there was simply a input resistance like this and a current source at the output like this. So this has a direct equivalence with the RE equivalent model. The approximate hybrid equivalent model has a direct equivalence with the RE equivalent model. Remember that the approximate hybrid equivalent model has a equivalence with the RE equivalent model, not the actual hybrid equivalent model. Why this is getting stuck, I don't know. So just let me see how well you remember the RE equivalent model of the common emitter and the common base. So for the common emitter and common base, the RE equivalent model was slightly different. So please remember the common emitter model and just tell me here what was the resistance that was coming in the common emitter model. common emitter RE equivalent model. That would be same as HIE. And here in terms of II or IB, there was a current appearing here. So what would be the HFE? That also you can say. So can someone give me this, what this would be? What is HIE? Beta RE. Very good, very good. So this shows that you have been following the lectures very well. So this is beta RE. And what is HFE? Not IB, only beta, because I is already here. So this II is IB, so II is already here, so HF is only beta. Normally you will find this HF parameter, HFE parameter given in the data sheet. Okay, so from the HFE you can say this, that is same as beta. If you need beta, you will go looking for the HFE parameter given in the data sheet. Now if you have the common base configuration, what would be HIB, HI, RE, simply RE. For the, yes, for the common emitter it is simply RE. What about HF alpha with a minus sign? Please remember that the direction of the current was opposite. So HFB would be minus alpha. Very good, very good. So HFB is minus alpha. So this is about the approximate hybrid equivalent model. Now if you are given the approximate hybrid equivalent model and then asked like you are asked to employ the approximate hybrid equivalent model to solve certain configurations, you can easily do that, because it is nothing but the RE equivalent model with these parameter values like this. So already we have shown the RE equivalent model analysis. The same goes well for the approximate hybrid equivalent model. But that is not true when you are working with the exact hybrid equivalent model. So when we are working with the exact hybrid equivalent model, then we have to do some analysis and I will not be doing the analysis once for common emitter and once for common base, but will employ the parameters as HI, HR, HF, H0 only, and when it is common emitter you would have to use HIE in place of HI. When it is common base you have to use HIB in place of HI. That's all. This is the beauty of making it as a two-port network, because these parameters remain same. Now first thing that would be easy to calculate here is the current gain. Actually we go for the current gain. So what we see is I0. Observe that I0, there is some problem in making this whiteboard move around. Anyway, so this I0, you see it is I is the current flowing through the H0, 1 by H0 resistance, this one, output admittance. Okay, so this I is that current, and another current HFIB is already there. Why it is called IB? It is II. Basically II is same as IB, the base current. Okay, and I0 is HI plus HFIB, and your I, this I is nothing but V0 divided by 1 by H0 or H0 V0, but V0 is nothing but I0 RL minus I0 RL. So from this equation what we get, I0 is minus H0 RL I0 plus HF II. This IB is II, so II. So we can directly get a relationship between I0 and II very easily. That's why we are going for the current gain first. So I0 we take in one side and then we divide I0 by II to get the current gain, which is nothing but HF by 1 plus H0 RL. Now I don't know whether you would like to remember the formula or solve for it. It is up to you. But it is quite easy to solve also. I don't know how easy it would be to remember, but it is quite easy to solve. So HF by 1 plus H0 RL, and in most cases you can simply treat it as HF when your H0 RL is much less than 1, because you already I have told you H0 is quite small. So H0 RL would most possibly be quite less than 1, but it depends on RL actually. RL, if it is a very high load, then it might not be so. So, but if RL is a moderate load or a very less load, then H0 RL would be quite small, and you can treat this current gain as the forward current transfer ratio HF only. Otherwise, just divide it by 1 plus H0 RL. Then comes the voltage gain. What is the VI? VI, you see, VI is this drop plus this voltage. So VI is this drop plus this voltage. So it is HIII plus HRV0. IIHI plus HRV0. Now note that II is already it is related to I0. II and I0 have a relationship like this, and I0 is also minus V0 by RL. So we use these things to replace II with I0, and then I0 is replaced by V0. So we get this thing. So there is a relationship coming out for VI and V0. So AV being V0 by VI, you can solve, and this is the relationship that comes out. Quite complicated one. So I don't know if you will remember this or go for solving this, but whatever be it, just remember the steps at least. Which are the steps to be followed to find this equation out? Otherwise, remember this well. Okay, but again there is a approximation. The approximation can be employed when your this term is much less than this term, then you can neglect this term, and the AV voltage gain becomes minus HF RL by HI, minus HF RL by HI. Okay, this thing. Input impedance you can also calculate. Input impedance is VI by II, that is the input impedance. Now VI is again HIII plus HRV0 using the KVL in the input loop. Now you have to replace this V0 with II with I0. So V0 is replaced as minus RL I0, and I0 you have to replace with II. We have a relationship. I0 is AI II. We are using the AI here, not the entire form, just AI. Now ZI is nothing but VI by II. So it is HI minus HR RL AI, and AI is this thing which you already have calculated. So ZI would be equal to, so if you put this thing here, this is ZI, and often you can neglect this because HR and H0 is very small. So you will be able to neglect this term, and ZI becomes simply HI, which is the input impedance of the hybrid parameter. That is the same as the input impedance of the two-port network. What is the output impedance? Remember, the output impedance of the two-port network is calculated when Vs equals to 0. So when Vs would be equal to 0, then your II input current would be, so let us see the diagram once. When your Vs is 0, when your Vs is 0, then in this branch, the input loop, you have one source here which is driving the current, and the resistances in the loop are Hi and Rs. So the current II would be this voltage divided by Hi plus Rs. So that is the thing written here in the output impedance. II equals to minus sign comes because of the directions, minus HR V0 by Rs plus Hi, and your I0 is already, I0 is HFII plus HFII is one branch which is the current source, and H0 V0 is the through the other branch, H0 branch, H0 V0, that is I0. So II can be now written in terms of V0, and Z0 can be found out by V0 by I0, which comes out like this. So if you solve it, it comes out like this. And now if you employ the approximation that this term is much less than this term, now you notice that H0 is already small, HR is also small. So one small quantity is compared with another small quantity, but as a whole it may turn out that this quantity is quite small than this quantity. If that is the case, then you can employ this approximation and say that the output impedance is nothing but 1 by H0, which is the output impedance of the from the hybrid equivalent model. Okay, so the output impedance of the two-port network is same as the output impedance of the hybrid equivalent model. So this is for the actual hybrid equivalent model. If you have to work with the actual hybrid equivalent model, these are the various things that we need to know. So we wish to, so this is the entire circuit, this is the hybrid equivalent model. We have connected the source and the load. With the source and the load, what becomes the current gain, voltage gain, input impedance, output impedance, that we calculated, we already calculated. And inside this, so this hybrid equivalent model is a BJT, either connected as a common emitter or a common base with its own various resistances and all. So you have to figure out, actually, for that particular BJT, you have to figure out what are its HI values, HF value, HR value, H0 value, that you need to employ here, and then you can work with this exact hybrid equivalent model and find out the different current gains in these terms. So this HF, H0, HI, HR, this has to be replaced by the actual configurations, H parameters. Normally things are not so difficult. In your examinations you will be able to employ the approximate hybrid equivalent model, but this is a theoretical part which may also be asked in the exams. Okay, this requires some derivation, so to tax your brain, this sort of question can also be asked. Now the last model is the hybrid pi model. Very easy, and it's what has been done, there are some capacitances and resistances included here. So this is just you have to just take it on face value that this is also a model of the BJT with so many resistances and capacitances coming in picture. The previous models were quite simple and were more logical to understand, but why suddenly all these resistances are appearing here with capacitances and all? To understand this, one needs to understand more of the actual physics behind the transistor. So we don't go into that, we just take this model as in face value and identify the different parameters what they are. R pi is called the input resistance, this one, and R pi is nothing but beta RE. R pi is nothing but beta RE. RE is nothing but beta RE is nothing but HFE. Beta is nothing but HFE and HI is nothing but beta RE. So these relationships you need to remember for working with the different models. So one parameter may be given, but you are actually working with another model. So you have to get the parameter of the model you are working in from the parameter which is given. So these relationships need to be remembered. Some of these relationships need to be remembered. They are easy also. R0 is the output resistance, which is nothing but 1 by H0. So these are same. RB is something that is new now here. What is RB? RB is the total resistance from the base contact, base bulk resistance, and something called the base spreading resistance. So you can say that this is a lumped resistance in the base side, but even then it is only a few ohms, very small. RU is a connection between the collector side and the base side, and this is called the collector to base resistance. This is quite large. Remember that R0 is quite large. Multiplying it with beta, it becomes quite large even, and this RU is even larger than that. It is in mega ohms. So, and it is obvious it should be in mega ohms, because we know that between the collector and base directly no transfer is happening, no current is flowing between the collector and base. So this is a resistor, this is a collector to base resistance. What are C pi and Cu? These are stray capacitances which are modeled and normally in picofarad range. So unless we are dealing with very high frequency signal, these capacitances can be assumed to be short circuited, open circuited, can be assumed to not be there unless we are dealing with very high frequency signals. And you can see that this, in this picture, the output side there is a current, it is a current source, it is a controlled current source. What is the control on this current source? You can say this is the IB dashed. So when the C pi is not there, IB dashed is nothing but the base current. So it is beta IB dashed. Okay, it is beta IB dashed, and that is same as GM V pi. So this IB dashed is producing a V pi current, V pi voltage across this resistance. So if this current source is related to IB dash, this current source is also related to V pi, because IB dash and V pi are related to each other linearly through this R pi resistance. So you can consider this controlled current source as either a current controlled current source or a voltage controlled current source. It is now your wish how you want to define it. When you are defining as a current controlled current source, we know that the relationship is simply beta times the input current IB. Here it is IB dashed, and when it is voltage control, now it is GM V pi. Some parameter GM comes in picture. So what is that GM? We need to see. That GM is nothing but 1 by RE. Remember this GM is nothing but 1 by RE. Okay. And there is another relationship here, just for your information, that R pi by R pi plus RU is almost equal to R pi by RU, because R pi is much smaller than RU, and this is nothing but HR. HR is the reverse voltage transfer ratio, if you have forgotten it. So our HR is the reverse voltage transfer ratio from the H parameters. So this completes all the different models of the transistor. Mainly we are working with the RE equivalent model or the approximate hybrid equivalent model, and we have seen that both are basically the same. There is a very direct relationship between those two. So with that note, I will end the chapter for BJT. So from tomorrow onwards, we will start with field effect transistor. There is another transistor that we need to learn, then that will end this course actually. So there are another type of transistors which are called field effect transistors, that we will start tomorrow. Okay, thank you, and I will close the meeting now.